Hi, my name is Yoojin and I'm a PhD student at the University of Stuttgart in Germany, and I'll be presenting my work in natural gradient shared control. Intelligent robots can assist humans to accomplish tasks in harsh environments such as disaster situations or outer space. However, robots cannot function robustly in full autonomy as these environments are complex and dynamic. We focus on shared control to effectively balance human control and autonomy to maximize the performance of the human-robot system. A common method is linear blending between policies where the arbitration is dependent on the confidence of the user prediction. However, mixed preferences from the users were reported, with some users preferring control authority over efficiency. Also, with poor intent prediction, the robot assists strongly towards the wrong goal, and the user fights against the assistance rather than to gain help. So how can we give more control authority to the user? Our motivation comes by observing the vector field of the robot policy. Here, the obstacles can be represented as a source where the vectors flow out of, and the goals can be represented as a sink where the robot should go in towards. Near these regions, the autonomous robot can take more control authority to ensure safety or precision. Elsewhere, the user can keep more control in regions where the field does not locally diverge. We later represent this using the Fisher information matrix. We formulate shared control as an optimization problem. The shared control action UT is chosen to maximize the user's internal action value function QH while keeping a proximity condition using the KL divergence, keeping the shared control policy pi-s closer to the autonomous policy pi-r. To solve this problem, we assume linear approximation of the objective and quadratic approximation of the KL divergence and express the problem using a Lagrange multiplier. This leads to a new control paradigm for shared control using natural gradient ascent. The state of the shared control system is updated using the previous state plus the inverse Fisher matrix times the gradient of the action value function with respect to the state scaled by the step size eta. Predicting a user-specific action value function can be challenging due to interpersonal differences. Instead, we consider the user action at each time step as a rough estimate of the derivative of the Q. Here, I will explain more about the Fisher information matrix. The Fisher information matrix, by definition, measures the expectation of the overall sensitivity of a probability distribution, the x given theta, to changes of a parameter. We focus on the fact that the Fisher information can be derived as the second-order derivative of the KL divergence. We utilize this to substitute the quadratic approximation of the KL divergence when solving the optimization problem. In our settings, the Fisher matrix expresses the sensitivity of the policy probability distribution pi action given state to small perturbations of the state. We estimate this to be the Hessian of the action value function. Note that in the paper, the action corresponds to the tangent of the state space manifold, for example, the position being the state and velocity as actions. As we consider action as an approximation of the first derivative of the Q, the Jacobian of the action becomes the Hessian of the Q, thus the Fisher information matrix. We focus on the two-dimensional setting where the position is the state. To compute the second-order derivative of Q, we use the first-order derivative of the actions computed using the finite difference method. The action velocities are easily queried from a neural network that infers optimal actions that the robot should take. For visualization, we can construct ellipses using eigenvalues and eigenvectors of the inverse Fisher matrix. The ellipse represents the direction that the user action should be stretched along. When the ellipse is close to a circle, the user has more control authority over the system. When the ellipse is narrow, such as near the obstacle, the robot augments the user's action towards a direction. In the videos, you can see that the computed ellipses of the inverse Fisher matrix points the direction to the goal, and the trajectory is augmented such that it avoids the obstacle with sufficient distance. For the autonomous robot policy, we trained a neural network that mimics optimal trajectories, which the network outputs normalized velocity and end-effector rotation at each time step. Since the robot policy is defined in task space, and we use inverse kinematics to compute the joint configurations, We use a multi-loss that includes inferring a grasping approach position in the state log partition function vs such that the policy indirectly learns to avoid joint configurations that would lead to collision. The right video shows the robot policy inferring the optimal direction towards reaching the red cylinder. To summarize, we propose an optimization method where the shared control action is chosen to maximize the human's internal action value function while constraining the policy to not diverge from the robot policy. We present an update rule which combines the user and the robot by stretching the user's action using the Fisher information matrix computed from the robot policy. We define a simulated teleoperation task to evaluate our method, where the user controls the robot arm to perform pick and place using the joystick. We hypothesize that our method allows the user to take more control during the task while ensuring safety and efficiency. We compare our method with different control methods, including direct control and linear blending. We use timid method defined in the stated reference for linear blending, and the obstacle avoidance is the minimal assistance towards obstacle collision avoidance. Our preliminary results from 16 users show significant improvement over other control methods while still maintaining compliance with user commands. When comparing the average task duration, our method showed the shortest duration with statistical significance. Our method also showed the lowest travel distance. However, it was statistically equivalent compared to direct control. We compare the average minimum proximity between the gripper and the obstacle as a notion of safety. The closer distance denotes that it is more likely to collide to the obstacle. Our method showed to provide highest obstacle avoidance compared to all other methods with statistical significance. We compare the cosine distance as the amount of disagreement between the user and the executed command. The average cosine distance of our method is significantly smaller than the linear blending, suggesting that the method performed actions closer to what the user intended, thus supporting our hypothesis that the method would allocate more control authority. Here we show trajectories of user demonstrations. As seen from quantitative results, direct control and obstacle avoidance trajectories exhibit divergence path compared to our method or linear blending method. Trajectories include dragging along the workspace boundary or approaching the place position from various directions. A noticeable feature in linear blending was when the assistance was often provided towards the wrong goal. Then the user had to fight against the assistance, and noisy trajectories are then present near the objects. We believe the results are convincing towards a better user experience, and we plan to further investigate this in our future work. Thank you very much.